and welcome to the Gasmet FTIR crash course. My name is Veikko Holksaari and I'm an application chemist at Gasmet Technologies. Today I will be your guide and explain to you what is FTIR and how it works. We will be mostly focusing on the gas analysis side. As a quick background, the predecessor of Gasmet, Teknik Instruments, was founded in the early 90s, and during these last couple of decades, we at Gasmet have grown to be a global leader in FTIR gas analysis. Our headquarters are located in Finland, but with our regional offices and distributors, we operate in over 80 countries around the world. So, what is FTIR? It stands for Fourier Transform Infrared with, you could say a silent word, spectroscopy at the end. And before we go any deeper, what is spectroscopy? It is the study of how matter and electromagnetic radiation, which is basically light, interact with each other. This usually means studying how matter absorbs or emits light or other radiation. So, what is electromagnetic radiation? When we talk about light, we usually mean visible light. However, this is only a small slice of the whole of electromagnetic or EM radiation. EM radiation is waves, which are characterized by their wavelength. On the right, we can see radiation with long wavelength, such as radio waves, and on the left, we can see radiation with short wavelength, such as gamma and X-rays. Radiation with short wavelength has high energy, and everything from high ultraviolet onwards has enough energy to affect humans in some way. This is the reason why you use sunscreen, to protect your skin from ultraviolet radiation. But in the middle, right next to visible red light, we can see infrared, and this is what we are interested in today. So, what is infrared? Infrared, or IR, is electromagnetic radiation with wavelength from around 750 nanometers to around 1 millimeter. IR is thermal radiation in a sense, because all objects emit infrared radiation, but the wavelength and the amount of radiation are dependent on the temperature of the object, and this is what thermal imaging is based on. However, this has nothing to do with infrared spectroscopy. It is based on the fact that infrared has this amazing effect of causing vibrations in a molecule. A molecule will absorb IR radiation and begin vibrating the bonds between its atoms. The energy and the wavelength of the radiation required depends on the atoms bonded, the bond type, and the type of vibration. Now, how those affect it is beyond this webinar. For us, it's enough to know that light corresponding to the molecule will be absorbed and other light will just go through. So, how is this used? Classically, we would use a so-called dispersive infrared spectrometer. Here, infrared light would be split by a monochromator. This is a prism or dispersive grating, which scatters light in different directions depending on its wavelength. Then we have a slit that only allows a small slice of light to reach the sample. And after the light goes to the sample, it reaches the detector and we get a reading. Then you would just turn the monochromator to allow the next small slice and keep going until you have checked everything you want. Now, a reading of what happens to light when it goes through a sample is pretty much useless on its own. We want to compare it to a reading of what happens if the sample isn't there. And there are two ways to accomplish this. One way is a so-called single beam operation. Here we first measure an empty sample cell to get a comparison measurement. This is called reference or background. Then we insert the sample and measure. We can also use a so-called double beam operation. Here, a device known as beam splitter is used to send half of light through the sample and half through an empty route as a reference. And after light goes to the detector, it would then compare the two signals and see if any absorption had happened in the sample. The evolution of technology now brings us to FTIR spectrometer, so Fourier Transform Infrared spectrometer. This method combines a Michelson interferometer, invented by Albert Michelson, and a mathematical function known as Fourier Transformation. FTIR has some advantages over the classical method. Most importantly, the measurements are faster and more sensitive. So how does this work? There is no monochromator to study one slice of light at a time. Instead, all wavelengths of light are used at the same time. The light meets a beam splitter, which directs the light into two halves at two different mirrors. One of them is fixed and another is moving. These beams of light then meet again, where they combine and go through the sample and into the detector. Now this is what we call a single beam operation. So to get a reading of what happens to light without the sample, first we have to do a measurement without a sample. With our devices, this is normally done once a day. And after this background measurement, we will compare all our other measurements to that background. So what is accomplished by measuring everything at once? Electromagnetic radiation is waves. When waves combine, in a way that they are just added together. This can be constructive, destructive, or anything in between. So when a beam of light goes into the Michelson interferometer, it's split in two. And these two waves go to two mirrors. And the location of the moving mirror can cause the other wave to be a bit ahead or a bit behind of the other one. And later, when they meet again, they form this combination wave. So, in FTIR measurements, this recombined wave goes into the detector, and we get a signal called interferogram. This is the signal as a function of the position of the moving mirror. The cool thing here is that because all wavelengths were measured at the same time, all of these data points have information on each of the wavelengths. So now we get to the Fourier transformation. Fourier transformation is a mathematical function that allows us to take a signal and see what frequencies form it. In practice, it takes a complicated wave and sees what simple waves are used to construct that complicated wave. Then it gives us the amount of each simple wave used. In our case, the interferogram is the complicated combination wave. Here we have two interferograms, one from the background and one from the sample measurement. By doing a Fourier transformation, we get the information on how much of each wavelength of light is present in that combination wave. So we get these two so-called single beam spectra for the background and for the sample. Now when we compare these two, we see what is the difference. So how much of each wavelength went through the sample compared to the background. This is a transmission spectrum. This can be changed into telling us how much of each wavelength was absorbed by the sample. And this is an absorption spectrum. And these are what we use here in Gasmet. So now that we have taken the measurement, what do we do with it? We talked earlier about how absorbed infrared light depends on the bonds and atoms. In different molecules, these are different, so different molecules will absorb light differently. This also means that the infrared spectra for different molecules are different, so they are like chemical fingerprints. So comparing infrared spectra of known compounds to our sample, we can determine which compound it is. Here we have examples of 4 different compounds, and you can see that their IR spectra are quite different. There is a small catch here, because not all materials can be seen with infrared spectroscopy. Single atom compounds like helium and molecules with 2 identical atoms like oxygen and nitrogen are invisible. And even very similar compounds have different infrared spectra. Here we have the 3 different xylenes. These all have the exact same atoms in almost identical arrangement. The only difference is where a certain small part is, whether it's in O, M or P position, and yet there are differences in the infrared spectra. And there's more. When light is traveling through material, the amount of absorption depends on the concentration of the material. This is known as Beer-Lambert Law. Here we can see a part of infrared spectrum of methane with 3 different concentrations. This means that if we have infrared spectra of known compounds in known different concentrations, we can determine how much of them there is in the sample. So in practice, we have the sample, and we have spectra of different compounds in different concentrations. Then we compare the sample to these different spectra, and we try to find a combination that fits the sample. This gives us the information of what compounds there are in the sample and how much. So, that's how it works. Now, how is this used? FTIR gas analysis has many different uses, and here are some examples. First off, emissions monitoring. Power plants, factories and such are required by law to monitor their emissions to prove that they don't pollute over legal limits. Next, Environmental monitoring. FTIR gas analysis can be used in greenhouse gas research, for example. And safety monitoring. With gas analysis, we can, for example, check shipping containers for toxic gases and keep people safe. So, FTIR gas analysis can be used in a variety of different situations with both organic and inorganic gases. This is due to the fact that while we at Gasmet have experience on measuring hundreds of different gases, there are hundreds or thousands more that can be measured with FTIR. So, all in all, FTIR gas analysis can be used in many different areas, and our mission here at Gasmet is to provide the necessary technology to protect the planet and everything living on it. Now, if you want to know more about FTIR, you can download FTIR technology white paper from our website. You can also contact us with any questions at contact@gasmet.fi. To get the latest news and updates, you can also follow Gasmet on LinkedIn, Twitter, Facebook and YouTube. Thank you for watching and be safe.